I welcome you all for this NPTEL online course on earthquake geotechnical engineering. Today we are going to have lecture number 47 and it is on slope stability in retaining walls, that is under module 5. We already covered slope stability and we are discussing retaining walls. 5 lectures we already discussed for the slope stability, and we will have another 6 lecture for retaining walls. So, one is already over, 46th lecture, which was an introduction to retaining walls is done. Today in this lecture number 47, we are going to talk about static pressure on retaining walls. That means it will be the, as far this module is concerned, this will be chapter 5 for this module, chapter 6 from this module, because 4 chapters was on slope stability and 5th one was on retaining walls introduction, and the 6th one is on static pressure on retaining walls. So, coming to after once we already introduced what types of retaining walls are there in the lecture number 46. And today we are going to deal exclusively with static pressure, because it is important before we go for dynamic loading or seismic loading, that how static pressure on retaining walls acts. When we talk about static pressures on retaining walls, popularly two theories, Rankine theory and Coulomb theories, are mostly used. I think during your undergraduate courses, you would have gone through this both the theories, which are particularly those are from civil engineering background, and the students who have taken as geotechnical engineering and soil mechanics, they are which is normally the compulsory course. Coming to these two theories, Rankine and Coulomb's theory, we will discuss one by one in detail. And before that, let me acknowledge that the major source of information in this lecture is from Kramer's book. When we talk about static pressure on retaining walls, the seismic behavior of retaining walls will depends on the total lateral earth pressure that develop during earthquake shaking. When we say total lateral earth pressure, that means it will include the static as well as dynamic. So, the total pressure include both the static gravitational pressures that exist before an earthquake occurs and the transient dynamic pressures induced by the earthquake shaking. So, response wall is influenced by both static as well as dynamic component. Static earth pressures on retaining structures are strongly influenced by wall and soil movements. So, for example, one is what you call active earth pressure, another is called passive earth pressure, and you may be perhaps already aware about that. That active earth pressure develop on a retaining wall when the wall moves away from the soil behind it, or we say the moves away from the backfill. So, as a result, it will induced extensional lateral strain, or we say the tensile strains in the soil, because the wall is moving away from the backfill or soil. So, it will try to pull the soil components. When the soil movement is sufficient to fully mobilize the strength of the soil behind the wall, then we say minimum active earth pressure act on the wall. So, there will be a minimum active earth pressure, and this minimum active earth pressure will be coming the point where the wall is that is enough to start the movement of the movement, fully mobilize the strength. So, at that point we say this is active earth pressure, maximum minimum active earth pressure. If we go beyond that, then it will be already failed. So, you do not require more than that, because very little wall movement is required to develop minimum active earth pressure. So, that is the difference. You require small active pressure. So, that is why it is called minimum active earth pressure. On the another side, when we discuss this passive pressure, this will be other way. So, retaining walls are usually designed on the basis of if you have the freestanding walls, retaining walls. Freestanding retaining walls are basically the walls on the both sides of the wall, there is no backfill. It is kind of a that normal wall. So, in that case, normally they are designed based on the minimum active earth pressure, but normally the retaining walls are not in the case where you have the freestanding walls. The second category, you may be perhaps aware that it is called passive earth pressure, and this develop on a retaining walls when the wall moves towards the soil or backfill, thereby producing compressive lateral strain in the soil. So, when the active earth pressure produced like tensile stresses, while the passive earth pressure produce the compression or compressive stresses and strains. Sorry. When the strength of the soil is fully mobilized, in this case maximum passive earth pressure act on the wall. So, in case of because here you can understand like this, in case of tensile stresses only minimum stress will required, because like basically you can say, you can understand it is like this: the soil initially have some compressive stresses, confining stresses, and when the tension starts, and it will be after minimum tension which is just crossing after 0 value, then your wall will fail. But on the compression side, this is not the scenario. Rather, on the compressive side, soil is able to take some compression, compressive load or compressive strength, but there will be a point which we can say the maximum which is related to maximum passive earth pressure, where the stresses the soil is unable to carry any more than that value. So, the stability of many freestanding retaining walls depends on the balance between the active pressure acting predominantly on one side of the wall and passive pressure acting on the other side. So, it is there. In fact, one side active pressure may act, another side the passive pressure may act, and accordingly it can be designed. Prediction of actual retaining walls forces and deformation is a complicated SSI problem. SSI means it is related to soil stress interaction problem, where you have the soil is involved, structure is your wall, and so that there is interaction between soil and structure, like that wall. So, it is both particular for dynamic loads. So, and it is not as easy problem. Deformations are rarely considered explicitly in the design. What is the typically for the design approach is to estimate the forces which are acting on a wall, and then to design the wall to resist those forces with a factor of safety which is high enough to produce acceptably small deformations. So, rather than, here point is this one, that rather than designing the wall based on the deformation, we estimate what is the forces which need to be resisted by this wall, and once these forces are known, then we consider for design purpose a factor of safety which is high enough, so that we can expect that this when we keep high factor of safety, that the deformation produced are small and they are within the permissible limit. So, it is this way that we design based on the forces rather than on deformation. However, we check that deformations are within the limits. A number of simplified approaches are available to evaluate static loads and retaining walls, and the most commonly used are Rankine theory, Coulomb theory. Then we have, so we will discuss these in detail, both Rankine and Coulomb theory in this lecture itself. Then the third, logarithmic spiral method and stress deformation analysis, we will discuss in the next lecture, that is lecture number 47, lecture number 48. So, let us talk about the first one, that is Rankine theory. In case of Rankine theory, what is the assumption? It was proposed by Rankine in 1857 and developed the simplest procedure for computing the minimum active and maximum passive earth pressure. By making assumptions about the stress conditions and strength envelope of the soil behind a retaining wall, that means when we say behind the retaining wall, that means backfill. Rankine was able to render the lateral earth pressure problem in a deterministic rather than because otherwise this problem is indeterministic and redundant, but with certain assumptions the problem can be deterministic and directly computing the static pressure acting on retaining walls. So, here the first of all in the Rankine, two assumptions are there. So, before I go ahead, I think two assumptions which are like it can be listed here. One assumption that wall is smooth, that is there is no friction, wall is smooth, that is the assumption. That means the friction between wall and soil is not considered in this case. Then the second assumption is wall is vertical. So, inclined wall is not considered, that means when we say retaining walls, it will be inclined, but not both sides. So, one side it will be inclined, so this is like this. So, that means this is wall is vertical this side. So, this is vertical, here is your backfill. So, it could be like this. So, this is vertical number one, and then you have the delta which is angle of friction between delta equal to 0 between this. So, with these assumptions, good point with the Rankine theory, it is able to deal with C5 soil, able to deal with C5 soil. That means it can be cohesive soils, or it could be the this sandy soil, or like what is say cohesionless soils, or it will be combination both. So, let us talk about active pressure condition first, then we will talk about passive pressure using the Rankine theory. For minimum active conditions, Rankine expressed the pressure at a point on both on the back of a retaining wall is given by this relation. It is the active earth pressure Pa, and what is Ka? Ka is the coefficient of minimum active earth pressure, where C is called cohesion and sigma V, you know that this is effective overburden pressure at a particular depth, because effective overburden pressure will not be constant, rather it will vary with the depth. So, as a result your Pa, this second quantity is constant, this does not depend on the depth, because C is cohesion is constant, Ka is depends on the phi. So, Ka is a function of, which we will discuss in the next slide, is a function of angle of internal friction phi of the soil. So, for a given soil, let us say if I consider the homogeneous strata, then the second term will remain constant, that is not going to change along the depth of the depth. However, sigma V prime is normally gamma into h, or gamma which is where h is a height, or I can say gamma into z. So, this will increase by the depth. So, as a result, here there are two terms, one term is constant in this equation, second term, while the first term increase with the depth. Now, what is Ka here? Ka is called the this is coefficient of active earth pressure, and when the principal stress planes are vertical and horizontal, as in the case of smooth vertical retaining walls. So, two conditions have come here, smooth vertical wall which retain a horizontal backfill. So, that means the backfill retained by the retaining wall is horizontal. So, this is the situation. So, this like backfill return is like this. So, it is horizontal. So, in that case the K value is given by 1 minus sin phi, 1 plus sin phi, which can also be written 10 square 45 minus phi by 2. So, that means what is phi? Phi is angle of internal friction of soil. So, using the value of phi, you can calculate the value of K. For the case of a cohesionless backfill inclined at an angle beta with the horizontal, if we assume C equal to 0, then, and if you have inclined case, inclined means if I incline this backfill by at angle beta, that means this is with the horizontal. So, beta is an angle which makes your backfill inclined, which is going here in clockwise anti-clockwise direction with the horizontal. So, backfill if I increase here, then the equation, this equation will be applicable when beta is beta should be less than phi, where phi is angle of internal friction. In this case, Ka can be found out from this equation, and this equation is applicable for the cohesionless backfill, though here C is not coming in both the equations. Now, if I put beta equal to 0 in this equation, then you see that when I put the beta equal to 0 in the second equation, then you will get the top one, because it will be 1 everywhere, and it will be 1 minus cos square phi, which is nothing but sin phi and root of that. So, here you get this equation, the top equation for beta equal to 0. So, that means the second equation Ka can be used for both beta equal to 0 as well as when beta is not 0. So, this way you can find what is called coefficient of active earth pressure coefficient. Continue with the active pressure. The pressure distribution on the back of the wall depends on the relative magnitude of the frictional and cohesive components of the backfill of the strength, which we will discuss in detail. Cohesive soils are undesirable. Why? As backfill material, as a backfill for retaining structures due to creep, stress relaxation and low permeability characteristics. However, sometimes you may not have choice, because you may have the natural material which may be cohesive, or it may not be cohesive, but that is not desirable as a backfill material, and as the simple result is because it is creep, stress reduction, low permeability. So, for example, in Rankine theory, active pressure case, when the C equal to 0, in that case the active earth pressure Ka is given from this relation tan square 45 degree minus 5 by 2. This is the diagram which shows for the cohesionless soils, and Pa active, because the first term, if you recall that in the Pa in general is given by K sigma b minus 2 C root K. If I put C equal to 0 in this equation, then you will get this equation Pa K sigma b is nothing but gamma z, it is replaced by gamma z here sigma b. So, this quantity is your effective overburden pressure, where gamma z should be taken as gamma d for dry soil, or it should be gamma submerged for the saturated soil. So, the sigma b, and so Pa and total pressure at the for this triangular, this is the pressure, active pressure, which is acting, which is varying with the z, but total pressure will be the area of this triangle, which will be half K gamma h square by 2. And where this Pa will act? This will act at 1/3 height. So, this will act at from the base, this will act at a height h by 3, and the pattern, the variation is here like triangular. This is the case when C equal to 0, when there is no C. The failure surface will make an angle with the horizontal 45 degree plus 5 by 2. Here you mind it, this angle is plus, while the negative sign is coming here in the K. So, K, for calculating the value of Ka, it will be tan square 45 degree minus 5 by 2, because for when phi equal to not 0. So, as a result Ka will be always less than 1, because tan 45 degree will be 1, or even using this expression also, when phi equal to 0, sin phi equal to 0, Ka will be 1, but when phi is not 0. So, as a result numerator will be less than 1 and denominator will be more than 1. So, as a result whatever you find for the real value of phi, K will be less than 1. So, that is coming from this equation or directly from this equation. So, that need to be understood. So, this was the case and then total pressure is given here, and this soil is gamma, phi and C equal to 0. Now, the second case, when we say phi equal to 0, that means no angle of internal friction, but naturally when phi equal to 0, C cannot be 0. So, as a result in that case the equation of Pa will be gamma z minus 2 C, because in this case phi equal to 0, then K will be 1 in this case as we discussed. So, K will be 1, tan square 45 degree, if I put phi equal to 0, it will be 1. Now, when K is equal to 1, then your equation become gamma z minus 2 C, because root K and Ka will be 1 here. This will be here, if z naught is the depth where the Pa becomes 0. So, to find the value of z, you can find by putting this equation 0 and solve for z equal to z naught. So, when you solve, then you get 2 C over gamma, that is the depth where your active pressure becomes 0. Coming to the total pressure, this is given by the first component gamma h square by 2 with K equal to 1 minus 2 C h plus 2 C square. So, this is the integration if you do from the, this equation along the depth, or you can say you find the net area, this area of positive area minus the top area. So, so the top area 2 C square y is this top area, like this is minus 2 C into h, because 2 C over gamma should be multiplied by the z naught, 2 C like we have z naught, and this is the here Pa need to be calculated at the top. At the top Pa will be simply minus 2 C. So, what will happen if I find the minus 2 C will be at the top. So, the area of this triangle will be minus 2 C, the top triangle will be minus 2 C into height into z naught. Z naught is 2 C over gamma divided by 2. So, you will get here this will be minus 2 C square over gamma. So, this is the term of this like area which will be coming, and then gamma h square by 2 minus 2 C h will be the area coming from the down. So, this way you find out the total pressure, calculate the total pressure, and because this minus is coming, so you need to subtract minus, because minus will be plus here, because this need to be subtracted. Then you have here if C phi soil, in case of C phi soil, your equation become gamma z square tan square. Again you need to understand this quantity is nothing but your K, and this quantity is root K. This is the same thing here. So, gamma z into sigma V naught into K and minus 2 C root K. So, this is the pressure given at. Now, you want to calculate the pressure at some depth. Z naught is the depth where your pressure becomes 0. So, again put this equation 0. So, once you solve, then you get 2 C over gamma tan 45, because basically you get 1 over tan, you need to understand 1 over tan 45 degree minus 5 by 2 is same as tan 45 degree plus 5 by 2. So, these both are the same thing. So, you get the value of Z naught is the tension cutoff, the point where your active pressure becomes 0, net active pressure. And once you solve, then you get this equation you solve PA total pressure gamma h square by tan square 45 degree minus 5 by 2. So, this is for C5 soil. In this case again the failure surface will make an angle 45 degree plus 5 by 2. When you have phi equal to 0, naturally this angle will become simply 45 degree. So, in this case 45 degree plus 5 by 2, 45 degree and 45 by with the horizontal. So, this was the case. So, how to deal with the C5 soil using the Rankine theory. Continue with this active pressure case. For dry homogeneous cohesionless backfill, Rankine theory predicts a triangular active pressure distribution which is oriented parallel to the backfill surface. The active pressure resultant act at a point which is located at h by 3. So, this is basically the case when you have the dry number 1. The second thing cohesionless backfill, that means you have the C equal to 0. When C equal to 0, we already said the total active pressure can be that is the area of the triangle PA K gamma h square. Because it is dry, so gamma will be in this case simply gamma d if you have the dry case, and K will be a function of phi, and K active earth pressure coefficient will be like that is less than 1. So, this was all about active pressure. In case of passive pressure, under maximum passive pressure condition, Rankine theory predicts that passive pressure at any depth is calculated. So, here two changes have occurred compared to active pressure. Instead of Ka you have Kp now, that is, and instead of plus sign you have instead of minus sign you get here the plus sign. So, this sign have changed here, where Kp is the coefficient of maximum passive earth pressure. For a smooth vertical wall retaining horizontal backfill, this is given by 1 plus sin phi, and this form is itself is saying when phi is not 0, when phi equal to 0 Kp will be 1. So, however, Kp will be always greater than 1. So, basically you can say that you can prove that for phi equal to 0, both K and Kp are same and the value is also fixed, that is 1. But when phi is greater than 1, then Ka will be less than 1 and Kp will be more than 1. In fact, for any value of phi, Kp you can prove that they are opposite to each other, 1 over K. So, or the product of K and Kp will give you 1. So, Kp can be calculated also once you find the value of K, it is opposite of K. So, this was the case when you have smooth retaining horizontal backfill, but if the backfill is inclined at an angle beta, that means this is the case, as we said, that is the backfill, inclined backfill for a retaining wall, and this angle is beta where you have backfill. In that case Kp is given by this relation. Again if I put beta equal to 0 in this relation, then you get the top equation for Kp. Continue with this passive earth pressure distribution for various backfill, as we will discuss the same thing, and total passive pressure for the case when C equal to 0. This is the case, this equation will be applicable when C equal to 0, is the similar form as we discussed for active earth pressure. There is no, when C equal to 0, in that case thus these things becomes easy for cohesionless soil, and this will act at h by 3 above the base, which is the similar case in case of active earth pressure. But different cases when C equal to 0, then your Kp is, it will be given by tan square 45 degree plus 5 by 2. Instead of minus, now you have plus. So, as a result your Kp will be, you need to understand that more than 1, Ka was less than 1, and the passive pressure at any depth, because Z, gamma Z is varying. So, Pp will increase with the Z with the depth. So, here Pp into Kp into gamma Z and total pressure is Kp gamma h square by 2. So, you have failure surface here and the failure surface will make in this case an angle 45 degree minus phi by 2. It was 45 degree plus phi by 2 in case of active earth pressure, but now it is minus phi by 2, and this total pressure Pp in this case will act at a height h by 3. So, this will be this distance will be in this case this total h is there. So, this will be h by 3 and the Pp is given from this relation which we have discussed. Continue when phi equal to 0, in that case this was the case when c equal to 0, but in case of when c is not 0, phi is 0, then phi is 0, that means you need to understand that nothing but Kp will becomes 1. So, that is the meaning of this, and the equation can be written simplify gamma into z plus 2c. Now, in this case you will not get any tension cutoff because both are plus. So, even at the top when z equal to 0, at the z equal to 0 also you get Pp equal to 2c, it is positive, it is not negative like earlier case. So, and the angle which makes failure surface will be 45 degree for phi equal to 0, and Pp in this case will be given by gamma h square by 2 plus 2ch. So, naturally when phi equal to 0, when you have this case, so this will increase, the C will increase the value of Pp. For the C phi soil, equations is given by here, and in both the equations the first term is nothing but Kp and the second term is root Kp. So, this was the pressure acting at any depth z, because z is varying. So, this first component will vary with the z, but the second component does not depend on the z, this is fixed. So, the second component is shown on the top even when the z equal to 0, tau c tau 45 degree plus phi by 2. So, this is the value, and the first component will increase with the z, and the maximum will be when z equal to h. At total pressure can be find out by the area of this vase, which is given by gamma h square by 2 tan square 45 degree plus phi by 2 for the first term, and the second term will be 2c tan 45 degree. In fact, you can say to find out this area of this total, you can say like this one. This is one rectangle and another triangle from here. This rectangle will have this 2c tan 45 degree 45 plus phi by 2 into h height, and this Pp will act somewhere between h by 3 to h by 6. It will not be now at h by 3, but little on that away. So, this distance is going to be more than h by 3 now. So, that can be work out on. In fact, how you can work out this rectangular will be middle of this rectangular area will act here, while the triangular will act at h by 3. So, the average will act somewhere between h by 3 to h by 2. So, this is the case. Now, in the case of Rankine theory, what happens when there is the presence of water? The presence of water in the backfill behind a retaining wall influence the effective stresses and hence the lateral earth pressure which act on the wall. And you know, when the backfill is present, the effective stresses will decrease. And so, for the wall design, the hydrostatic pressure due to the water must be added to the lateral earth pressure. So, hydrostatic pressure need to be added to the lateral earth pressure, because the total lateral thrust on a wall retaining a saturated backfill is considerably greater than that of a wall retaining dry backfill. You have a saturated backfill, naturally gamma saturated will be always more than the gamma dry. So, if you saturated, gamma saturated will be high. So, what will happen? The wall need to protect the more weight on the lateral direction. As a result, the provision of backfill drainage is an important part of the retaining wall design. So, because the earth will apply more pressure on the wall when it is saturated compared to dry. So, in that case we need to either provide some drainage system to avoid this water problem, otherwise we need to design thicker wall. So, this was all about Rankine theory. Now, we quickly discuss Coulomb theory, which is in Coulomb theory what is done. Coulomb in 1776 was the first to study the problem of lateral earth pressure on retaining structures. By assuming that the force acting on the back of a retaining wall is resulted from the weight of vase of the soil above a planar failure surface, Coulomb used force equilibrium to determine the magnitude of the soil thrust which is acting on the wall for both minimum active and passive maximum passive condition. First of all, Coulomb theory, one difference compared to Rankine, here we will assume that C equal to 0. That means, this theory we are going to discuss only for cohesionless soils, not cohesive soils. So, compared to this Rankine, this is the limitation of this. However, what is the positive point for this theory? In the Rankine theory, we assume that wall is smooth and vertical. In this case, it is not necessary that your wall should be vertical as well as smooth. Since the problem is indeterminate, a number of potential failure surface must be analyzed to identify the critical failure surface. That is the what is the critical failure surface? That is the surface that produces the greatest active thrust on the smallest passive thrust or smallest passive thrust. So, here in active pressure condition, this is a scenario in the Coulomb theory. Under this is here under minimum active earth pressure condition, the active thrust on a wall with the geometry which is shown from the force, this geometry is obtained from the force equilibrium. Here what you have, this is the forces acting on the wall. First of all, compared to the Rankine theory, understand that this wall is not vertical on this side, backfill side, rather it makes an angle theta with the vertical, one thing. Second thing, there is a angle of internal friction between wall and soil, this is wall and soil, here it is delta. So, this angle is not 0 which was considered earlier delta. So, and the failure surface will make an angle alpha with respect to this alpha angle A will be with respect to horizontal. What is W? W is the weight of the this vase, and this will act always, W always act vertically in downward direction. Now, when you have, and this is the total force F which is acting on this vase, we will make an angle phi with respect to the normal to this surface, and alpha is the angle which your failure surface, this failure surface will make with the horizontal. We do not know value of alpha A which can be determined. Other things theta, delta, phi, beta, all other things are known. Beta is the angle which the surcharge is inclined with respect to horizontal. So, everything is known in this case except alpha A and this Pa. Pa is the active earth pressure, W will act in the downward direction, F is acting along this direction. If I join from this point to this point, this is Pa, direction of Pa which is acting here. So, this is parallel to each other. How the Pa is given here? Pa is given by half K gamma h square. This is the similar equation, exactly similar equation as we discussed. This is for cohesion soil first of all, this is C equal to 0. So, the equation is same as we discussed in Rankine theory, but what is basic difference? K in this case is given by this relation cos square phi minus theta cos square theta. So, here earlier in Rankine theory only phi was involved, but here you have theta, delta and theta, two more parameter have come. Earlier beta was there also, but two more parameter, that is delta and theta have come in picture here, where delta and theta we already explained what is delta and theta. Delta is this angle which makes, and theta the wall is not vertical. So, theta could be 0 if your wall is vertical, and delta could also be if you consider the smooth wall. So, this was for active pressure. Here in this case alpha A is given from this relation phi plus tan square tan phi minus beta plus C1 and C2, and there are long equation for C1 and C2 which are again function of phi, beta, theta, delta, all 4 angles. 4 angles in this problem involved delta, theta, beta and phi, but all 4 are known, and this alpha is unknown which can be found out from this equation. This was active pressure. On the same line you have active pressure, passive pressure also for Coulomb theory, and this is again for cohesionless backfill, that means when C equal to 0. In this case this equation is also similar to what we discussed for Rankine theory, but Kp will be given from this relation, and the angle which it makes alpha p with the horizontal can be found out in this case using this relation phi plus tan phi plus beta C3 C4, where C3 and C4 are given from these equations which are function of again 4 angles phi, beta, then you have theta and delta. So, all are unknown, then you can calculate the value of alpha p. Here in this case for passive pressure the vase will be like this, W will act, and again the F will act with an angle phi similar to that, but PP earlier was acting in the downward here, but now the direction of PP is changed. So, this angle will be, in this case this angle will be delta. So, if I draw the force polygon, then W will always act vertically, it was same and active as passive pressure, and F is acting along the direction F, and then from I join from this point to this will be the direction of PP, that is passive earth pressure. So, this was all about Rankine theory and Coulomb theory. We have come across the value of delta in these equations, which is a friction angle between wall and soil. The delta depends on your material. If you have concrete, massive concrete of the wall 17 to framed concrete, so range is 17 to 26. Steel sheet pile, it will reduce because piles will be steel will be smooth, so 11 to 17 degree. So, accordingly we can select the values. Thank you very much for your kind attention.